Okay, so if you take a look at the do now, this is a recap of what we were talking about yesterday. Use a local linear approximation to approximate the value of the cube root of 25. Okay, so what function are we dealing with? We're dealing with the function that is the cube root of x. Okay, is the cube root of 25 going to be an exact value? No. So here's where it comes into it, where you have to kind of like make a decision yourself. You have to stay close to 25 with what's actually a perfect cube root. So the closest thing to 25 that's a perfect cube root is actually 27. So therefore, I'm going to choose a equals 27, and I'm going to make my tangent line based off of that. Just to point out, f prime of x, okay, again, I'm taking the derivative of x to the 1/3, theoretically, is 1/3 x to the negative 2/3, or 1/3 cube root of x squared. Okay. So remember, L of x is equal to f of a plus f prime of a times x minus a. In this particular problem, L of x is equal to f of 27 plus f prime of 27 times x minus 27. Why 27 and not 25? 25 is not a perfect cube root. You're choosing the closest value to 25 that is a perfect cube root, again, whatever's the closest. So L of x is equal to f of 27. It's a fancy way of saying the cube root of 27, which is 3. F prime of 27. So that's me plugging in 27 into this expression. 3 cube root of 27 squared. So that's 1/3 times 3 squared, or 1/27. Okay? And then x minus 27 stays as is because you don't have an actual x to plug in just yet. So now you have your tangent line. 25 is relatively close to 27. It's not exactly there, but it's pretty close. So I would say you'd probably get a pretty good approximation for the f of 25 by doing the L of 25. So you're going to plug 25 in for x in that linear approximation model like I just highlighted before. So L of 25 is equal to 3 plus 1/27 times 25 minus 27. Again, I don't mind if you use your calculator right now, because again, the idea is not calculation. It's more about setup and drawing conclusions. But again, that wouldn't be terrible if you did have to do that one by hand. But again, just for the sake of time, 3 plus 1/27 multiplied by 25 minus 27. 25 minus 27 comes out to be 2.9259 repeating. Okay, so we're saying that comes out 2.926 if I were to round it to 3 decimal places. This is our approximation. Okay, how good is that approximation? And not that you always have to do this, but as I had mentioned before, if you wanted to check, this again is our approximation using the tangent line. 25, 27, they're relatively close to each other. Again, this idea of good and bad as relative. But if I actually go and check 25 to the 1/3, comes out to be 2.924, 2.926. Those are pretty close to each other. Okay, so the point is the tangent line will yield a pretty good approximation. Well, as I mentioned, the name of this unit is approximations. And one of the other ways that you can do an approximation is using something called differentials. At the end of the day, it's basically the same thing as making a tangent line. So as long as it doesn't specify to use differentials, you could still use the tangent line like we did before. But I still want you to understand what differentials are and how they apply to these problems, because they have a greater meaning at some point as we go through our course. Okay, so if you go back to when you were in your first algebra class and you ever learned about the slope, if you remember, delta y over delta x is how we calculated the slope between 2 points. And when we started getting into calculus, we called that the slope of the secant. The secant is basically a line that goes through a curve at 2 separate points. And again, if you take the change in y and divide it by the change in x, that's how you were able to figure out how steep your line was. Okay? So when we started turning this into the derivative, we end up having the notation dy over dx. And again, it kind of feels like delta y over delta x because it is actually pretty close. The way it's actually truly defined is if I were to make delta x really small, and I take a look at what happens with delta y, as I merge those together, they become the slope of the tangent line. So if you take a look at the example I have on the right-hand side, again, initially this is the secant. as I start sliding this point, okay, along my curve, eventually I get to a point where I have the tangent, in other words, f prime of x. And what you'll notice is that, let me change colors just to show you, delta y is the original change in y when I was thinking of it as a secant, but it eventually merges to become dy, which is the differential version when I'm actually at the point of tangency, okay? So essentially, again, delta y, dy, similar. Delta x and dx actually are exactly the same. They don't change at all. Even as I move this point closer and closer and closer, the delta x and the dx are going to stay the same. Okay, so I'm actually going to change up a little bit of the questions that I have below, and then I'm going to draw, like, write out what the conclusion is as we get to this point. So instead of saying why is this significant, I want to say, what is the difference between delta x and dx? Okay, so for the calculations that we're doing, nothing. Delta x and dx is always going to be whatever the change in the x value is that we're working with. What is the difference between delta y and dy? Okay, basically delta y is how the y values change along f of x, whereas, whoops, I did not mean for that to come up, whereas dy is how the y values change along f prime of x. Okay, and using dy is going to yield better approximations because you're talking about almost like infinitesimally small values or changes in the value of x and the value of y. So that's the thing I want you to get out of this. I know the notation is going to be a little confusing, but what I want you to do is think of dy and dx similar to delta y and delta x, except for the fact that they are like infinitesimally, well, dx is infinitesimally small. Dy might not necessarily be, but it's going to be a very small change in y. And again, we're going to use these as ways to do our approximation. Okay, so basically what's going to happen with the above picture, and this is the conclusion of what we were trying to draw from this image before, as Q approaches P, okay, so as this point on the right-hand side gets closer and closer and closer to the first point, delta x, which is dx, approaches 0, okay, and delta y becomes dy. So you might be wondering, Sonia, why you're going through all this notation, how does this actually deal with doing approximations? So basically, if you were to write out this differential form of the derivative, okay? So remember, there's different notations to represent the derivative. We often use f prime of x, but we know this as dy dx. Well, instead of thinking of dy dx as its own little unit, you're now going to think of dy separate from dx. So imagine that you like cross-multiplied at this point, right? You'd have dy on the left-hand side equals f prime of x dx. Well, this is the model we're going to use when we want to do do approximations with differentials. dy is what we're going to be calculating. Okay, we're going to have to add that onto something. F prime of x is going to be the derivative of whatever function we're dealing with, and dx is going to be the change in the x values. So when it asks you to find like the differential form of each function, it's basically asking you to put it in the form of dy equals something dx, similar to what I have highlighted in orange above. So mostly this part is just a matter of practicing with your derivative rules before we hop into actually doing, drawing conclusions with this. So take a look at letter A, okay? This originally starts as y equals e to the 3 minus x to the 4th. To find this in, or to put this in differential form, that means I want to put it in the form of dy equals f prime of x dx. So to put something in differential form, you're just going to take the derivative. The derivative of y is 1 dy, so I'm going to leave it on the left-hand side. F prime of x, if this was my original f of x, then when I take the derivative of e to the 3 minus x to the 4th, remember the derivative of e to the u is e to the u du. So let me write that out. Derivative of e to the u equals e to the u. I don't know why I put that extra equals. du. Okay, so this would be e to the 3 minus x to the 4th, and then the derivative of the u, in other words, the exponent, is negative 4x cubed. And then again, dy equals f prime of x dx. This is your differential form of that function. Okay, so finding the differentials is essentially finding the derivative and just making sure that dx is on the right-hand side. You can almost think of it like when you did implicit differentiation, where you followed up every variable with d of that variable, kind of similar. Now we start to get into actually doing some of the approximations with this. And again, the idea is showing how you can use different forms of calculus to do approximations. Ideally, these would be used when you didn't have a calculator or the computation was too hard. It's okay to use your calculator, okay? Because right now we're just trying to get the concept of what these things are, not showing me that you can do computations by hand. So suppose you have the function f of x equals 3x squared minus 8x plus 2. Find the true change in y, which is delta y, as x goes from 1 to 1.01. Then use the differential form to approximate the change. So what I'm going to show you here is the true change in delta y, the true change in the change in y values, and then you're going to use to approximate the change using dy. Okay, and I want to show you how these kind of come out close to each other. Okay, so as x goes from 1 to 1.01, delta x is the change in my x values. So I'm going to do it from 1.01 minus 1. You're always going to be the one that it goes to minus the one that it starts from. So that's 0.01. As I mentioned before, delta x is dx. So when I eventually use dx, I'm going to still use 0.01. Okay. So let's start with the true change in y. So in my calculator, I'm going to do the f of 1.01, and I'm going to subtract from it the f of 1. Imagine trying to do this by hand. You'd have to do 3 times 1.01 squared minus 8 times 1.01 plus 2. I don't know about you, but that to me is not a very easy calculation. That's the whole point of what we're trying to learn here. We can eventually use dy to approximate delta y in situations like this, where if I didn't have a calculator, this would be a really tough approximation. But as I also said before, I'm not talking about learning how to do computations. What we're trying to do is show how differentials give you a pretty good approximation. So I'm going to use my graphing calculator to actually calculate this value. So I'm going to go to y equals, go back to y1, and I'm going to type in the function we're dealing with, 3x squared minus 8x plus 2. Okay, so when I want f of 1.01 minus f of 1, alpha trace, okay, select y1, y1 of 1.01 minus y1 of 1. The real change in my y values is negative 0.0197. That's the true change in my y values. Okay. What I would like to do now is show the approximation of that change using this idea of differentials, okay? So I'm going to come back and I'm going to compare this to negative 0.0197. That's what we're going to compare this to. So put that number out of your head for just a second. Okay, so y equals f of x equals 3x squared minus 8x plus 2. If I put this in differential form, it's basically taking the derivative. Y becomes dy, 3x squared becomes 6x, 8x becomes 8, plus 2 becomes 0. And again, you want to follow that up with dx. Almost think of it like when you did implicit differentiation. Take the derivative of each side, follow up dy on the left-hand side, follow up dx on the right-hand side, and now you're going to plug into this. Okay, so our approximate change in y is going to end up being this dy. So we're going to plug in 6 times x. The x that we are focusing on is x equals 1. I don't know if this is the best way of putting it, but like look at the easier of the two values to do a calculation. Is it easier to calculate a value with 1 or 1.01? That's why we're using 1 as our x. It's also the one that we're starting at. That's basically where this is coming from. So if I do 6 times 1 minus 8, and I multiply that by dx, which as I said before is the same as delta x, 0.01. 6 minus 8 is negative 2. Negative 2 times 0.01 is negative 0.02. Okay, think about how easy that calculation was for dy. It was so much easier to do it by hand than if I had to do some sort of other calculation. And now what I want you to compare it to is the value that we had gotten in the calculator by doing y1 of 1.01 minus y1 of 1. Negative 0.0197, negative 0.02. Those are pretty close to each other, right? What was an easier calculation? Plugging in 1.01 into this whole function and then subtracting what happens when you plug into 1 into that function, or taking the derivative of each side, plugging in the value you're starting at, plugging in the difference in the x values, and what value you get is an approximation for that change. You once again can see dy is close to delta y. Okay, and basically why is that? That's because 1 and 1.01 are pretty close to each other. But again, you're using differentials to do an approximation. Okay, so I want to skip ahead to the example where it says use differentials to approximate the square root of 10. There's more explanation that goes into it, but sometimes I feel like over-explaining doesn't always work so well. So I basically want to show you an example of how would you use differentials to do an approximation. Okay, so here's what you have to think about. You probably can give me a decent approximation for the square root of 10. What is 10 close to? 9, right? Square root of 9 is 3. So I would say that our answer is probably something that's a little bit bigger than 3, right? But what if I want a more exact answer than just saying a little bit bigger than 3? This is where using a tangent line or differentials to do an approximation would come into play. So you need to have some sort of an f of x for this problem, something that you could take the derivative of and do the differential form. Well, think about it as the function that's being done to a number. So in this problem, 10, you're taking the square root of 10, so the square root of x is your f of x. Okay. Your x sub 0 or whatever your approximation is, like where you're going to end up making your tangent line or, doing your differential value, is the value that's closest to 10 that is actually a perfect square. But again, whatever is closest because 10 doesn't work. So I would say in this case, my x sub 0 is 9, okay? Because 9 I do know the perfect square values for. So I now need to find my delta x value. And it's from whatever you're actually doing the calculation with. So you're technically plugging 10 into square root of x. So my original x value is 10 minus whatever value you're trying to get to, whatever the perfect square value is, okay? So when I do that, I end up getting a value of 1. As we mentioned in the previous example, delta x and dx are technically the same thing, okay? So where you're trying to do the approximation, minus whatever the closest value is that comes out to be a perfect square, or in other cases a perfect cube, or whatever it happens to be. All right, so now you're going to write f of x equals the square root of x in differential form. Okay, so I'm starting with something like y equals the square root of x. When I take the derivative of that, dy equals 1 over 2 radical x dx. That's my differential form that I'm going to plug in to approximate the change in y. Okay, well, how does that actually yield in an approximation, for radical 10? Our actual approximation value is going to come from y plus dy. The y value at the point where I actually know the square root of some number, plus this dy, some difference in y values, and that's going to give me the value of my approximation. So the square root of 10 is going to come from the y value, again, at the location where I know the square root. So if I take the square root of 9, that comes out to be 3. That's my y value. Okay, I know square root of 10 is going to be either something a little more or a little less than 3. I hope it makes sense. It's going to be a little more. So likely it's probably going to be that my dy comes to be a positive number. So how much do I have to add to 3, though, to get a decent approximation for square root of 10? That's where dy comes into play. So back on the left-hand side, dy comes from doing 1 over 2 square root of x. X is 9 because, again, that's the perfect square I chose. You don't want to put 10 in there because then you're back stuck with, what do I do if I don't have a calculator? Dx happens to come out to be 1, so I end up with 1/6 as my value. So my dy is 1/6. I could obviously use, combine this together to make a fraction. So that would be, 18 over 6. So 19 over 6 is my approximation. To give you a better idea of how good that approximation is, 19 over 6 comes out to be 3.16 repeating. Okay, so about 3.167, that's the value of our approximation. We're saying radical 10 is about 3.167. So just using this idea of differentials, we got a better approximation than just saying square root of 10 is something that's a little bit bigger than 3. Okay, so the true value of radical 10, if you want to compare it to it, if I go on my graphing calculator and I type in square root of 10, I get 3.162. Okay, 3.167, 3.162, those are pretty close to each other. And again, the 3.167 I got completely without using a calculator. So again, I'm able to approximate something that's not a perfect square to more accurate than just saying a little bit bigger than 3 by using this idea of differentials. Find a y value at a point that's close to 10 and give me the exact value. Find one that's easy. Add this, difference in y, which is what this dy is calculating, and I'm able to get a good approximation for a specific value. All right, so let's try another one. Let's do number 4, just to do one that with like a slightly different value. So I have e to the negative 0.01. That's the value that I'm trying to approximate. Let's think about what kind of function does this sort of look like. I would hope that it makes sense that this sort of looks like e to the x. The closest value to negative 0.01 that I probably know the exact value for e to the x in would be x equals 0. Okay, so I'm going to use that as like my initial point. My delta x is going to come from what I'm technically plugging in that I'm trying to approximate, negative 0.01 minus whatever my x is, x equals 0 in this case. So negative 0.01 is going to be my delta x, which is also dx. Okay, your approximation is going to come from y plus dy. Okay, y being the value I get when I plug in the x that I chose into my f of x. So in this case, e to the 0, which is 1, that's my y value. So I know e to the negative 0.01 is going to be something close to 1. A little more, a little less, I have to figure that out. dy is going to come from finding the value of the differential. So if I think of the function y equals e to the x, that's just f of x equals e to the x and y equals e to the x form. My differential form would be taking the derivative of each side. And again, as you take the derivative of a value, follow it up with dy or dx. And now let's plug into that. dy is going to come from e to the 0, x equals 0. dx was negative 0.01. E to the 0 is 1. So this ends up coming out to be negative 0.01. So I take the y I had calculated plus dy, which is plus negative 0.01, which comes out to be 0.99. This is what I'm saying is my approximation for e to the negative 0.01. Okay, so e to the negative 0.01. That's what I was trying to find the approximation for. Not an easy number in your head, but again, hopefully you would make sense that this is going to be something close to 1. If I actually now go on my calculator and I do second ln negative 0.01, you can see 0.9900, 0.99, our approximation came out to be very close. Okay? There will be times where it will specify if you have to use differentials or linear approximation. At the end of the day, they're going to come out to be the same thing. So if you prefer to do it by linear approximation, you're still going to get a good approximation using the tangent line. But again, I'm just trying to show you various forms of doing an approximation intended for situations that are either computationally too difficult or you don't have a graphing calculator.